Today we're going to talk about inverse of functions. When you think of the word inverse, you might think back to solving equations when it says something like x plus 2 equals 4, you subtract 2, because addition and subtraction are inverse operations. Multiplication and division are inverse operations. A lot of times we call those opposite operations, so maybe the word inverse brings up the word opposite in your mind. If you were to type in your calculator sine and input 30, if you're in degrees mode, you would get an output of 0.5. But if you were to type in inverse sine, that would be second sine, and your input is 0.5, you're going to get an output of 30 degrees. So what inverse does is it switches the input and the output. So an inverse switches the input and the output. So let's look at example 1. For the function f of x equals x squared. So that means whatever our input is, we're going to square it. Negative 3 squared, negative 2 squared, negative 1 squared, 0 squared, 1 squared, 2 squared, and 3 squared. And we'll graph each point and plot this function. We'll do it in solid. We'll do the inverse dotted. 0, 0, 1, 1, and negative 1, 1, 2, 4, and negative 2, 4, 3, 9, and negative 3, 9. So that's a parabola. The f inverse of x, this right here means the inverse, just means that we switch the inputs and the outputs. So each point, the x and y value get reversed. So when we graph the inverse, it's all the x and y values reversed. So we have 0, 0, 1, negative 1, and 1, 1, 4, negative 2, and 4, 2, 9, negative 3, and 9, 3. So we'll dot in the graph of the inverse. Now, this should remind you of the symmetry test for symmetry about y equals x, because for that test, we switch the x and the y, because for every point x, y, the point y, x also exists when there's symmetry about the y-axis. And if we draw in the line y equals x, we should see that the original function and its inverse are symmetric about y equals x, so that y equals x is a line of reflection. On this original function, f of x equals x squared, there's no place I can draw a vertical line and touch it twice. So this is a function. But on the inverse, if I draw a vertical line, I can draw one that touches it 2 times. So the question, is that inverse a function? The answer is no, it is not a function. Example 2, find the inverse of the function y equals 2x minus 6. Before we do that, let's graph y equals 2x minus 6. It's got a y-intercept of negative 6. So we plot that y-intercept. It's got a slope of 2, so it goes up 2 and over 1. And we'll plot as many of those as we can so we make sure we maintain our slope. So there's y equals 2x minus 6. To find the inverse, what we need to do is switch the input and the output. So we have x equals 2y minus 6. And we're going to solve that for y in order to find the inverse. So we're going to move that 6 over to the other side. It becomes x plus 6 equals 2y. And we're going to divide both sides by 2. So I have y equals x plus 6 over 2. But I'm going to try to graph this, so I'll put it in slope-intercept form. X over 2 is 1/2 x plus 6 over 2 is 3 equals y. So I have a y-intercept of 3. And a slope of 1/2. So I'm going to go up 1 and over 2 and fill in as many of those as I can on the graph. And I'll dot the inverse. In this case, in the original function, there's nowhere I can draw a line that touches twice, so it is a function. There's no place I can draw a vertical line that touches this one twice either. So is the inverse here a function? The answer is yes. So the inverse sometimes will be a function, sometimes it will not be a function. And we should notice again, if I put in the line y equals x, that's a line of reflection. So anytime I draw a function and its inverse, we should notice that it is symmetric about y equals x. Example 3, we are going to graph the function p of x equals x cubed. So if I start plugging in some inputs, I put in 0, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, and negative 2 cubed is negative 8. I'm going to dot this one because my answer on the graph is going to be after the transformations. So if p of x is x cubed, then p inverse of x is going to be the cubed root of x, which means this right here is the inverse. So our first transformation is the inverse. That means we're going to flip the graph over the line y equals x, which also means every point x, y is going to become y, x. So the point 0, 0, I'm going to turn that around and it's still going to be 0, 0. 1, 1 is going to stay 1, 1. Negative 1 is going to stay where it is. Then the point 2, 8, when I turn that around, I'm going to get 8, 2. And the point negative 2, negative 8 is going to become negative 8, negative 2. So here it is after the first transformation. If we draw in the line y equals x, we should be able to see that the two are symmetric about y equals x. So that's the graph of the inverse. But there are two more transformations. Inside the function is a -2, so the second transformation is that this graph shifts right 2 units. And then outside the transformation is +3. Outside the function is +3. So the next transformation is that it shifts up 3 units. So I can take each coordinate on this inverse and move it 2 to the right and 3 up. And that will be the final graph of this function. Example 4, given f of x equals 5x minus 7, find f inverse of x. We're going to find the inverse. F of x equals is the same as saying y equals, it's just in function notation. In order to find the inverse, I'm going to switch my input and my output. So I'm going to have x equals 5y minus 7, and I'm going to solve for y. So I'm going to move that 7 to the left. X plus 7 equals 5y. And then I'm going to divide both sides by 5. Now I'm not graphing this, so I really don't care if it looks like slope-intercept form. So y equals x plus 7 over 5 is okay. But for my final answer, I'm going to go back to function notation like it was in the beginning. F inverse of x equals x plus 7 over 5. So that's my inverse, but before I put a box around it and say it's definitely true, I am going to verify that the original function and what I just found are inverses of each other. And here's how you do that. To determine if that truly is an inverse, I have to evaluate f of what I'm saying is the inverse of x, which means I'm evaluating f of x plus 7 over 5. And what that really means is I'm taking that x plus 7 over 5, and I'm going to plug it in right there for x, and then simplify it. So 5 times, and then the x becomes the inverse, x plus 7 over 5. And then I still have a minus 7. But this is 5 over 1 times x plus 7 over 5, and those 5s do cancel. So I get x plus 7 minus 7. Plus 7 minus 7 cancels. So I'm left with x. So f of the inverse of x equals x. Or we can think of it like this. Y equals x. And there should be symmetry about the line y equals x. So if I can simplify down to just an x, that tells me my inverse is correct. Now that verifying kind of has a lot to it up here. So to put it in maybe some simpler terms, in order to verify it, I take what I find here and plug it in here. That put me on this line. After just a couple steps of simplifying, I got down to nothing but an x. That verifies for me that my inverse is correct. Go ahead and pause the video for a moment and try this last problem. So this is my y, and I need to switch the x and the y in order to find the inverse. So x equals 1/2 y plus 3/8. Now I need to solve for y. So I'm going to move this 3/8 to the other side. X minus 3/8 equals 1/2 y. To eliminate that 1/2, I can divide by 1/2. Probably the easier way is to multiply by the reciprocal. So I'm going to multiply both sides by 2. And that will cancel out that 1/2 for me. And then I'll distribute this 2. 2x, and this is 2 over 1. So 2 over 1 times negative 3/8 is negative 6 over 8, which is 3/4. Back in function notation, f inverse of x equals 2x minus 3/4. I'm going to plug that inverse into the original function and see if it can simplify down to x. And if it does, then I know that this is correct. So 1/2 times the inverse, 2x minus 3/4 plus 3/8. We'll distribute the half. 1/2 times 2 is 1, so 1x, minus half times 3/4 is 3/8, plus 3/8. Minus 3/8 plus 3/8 cancels. I'm down to just an x, which tells me that what I decided was my inverse is correct.
So let's end this with a little review of symmetry in functions and transformations of functions, just so we can keep those things fresh in our mind. So our first question here, y equals negative 3 over x, we want to know, is that symmetric with respect to the x-axis? If it is symmetric with respect to the x-axis, then it will be symmetric vertically. So for every y that exists, the opposite of y will also exist. So we do opposite of y. Okay, now, can I algebraically make both sides equal the original? So if I multiply both sides by negative 1, I get y equals 3 over x. I got the left side to match the original, but not the right side, so I'll have to say there is no symmetry with respect to the x-axis. How about the y-axis? So if there's symmetry about the y-axis, then it will flip horizontally. So for every x value that exists, the opposite of that x value will exist. So we get y equals negative 3 over negative x. And when I simplify that, it's y equals 3 over x. The left side matches the original, but the right side does not. So I'm going to have to say no symmetry with respect to the y-axis. So how about y equals x? If y equals x, then x equals y, so I can switch the y and the x. So that should actually be a y there. So x equals negative 3 over y. Now, if I multiply both sides by y, I get yx equals negative 3. And I can divide both sides by x, and I get y equals negative 3 over x. And I was able to algebraically make the left side match the original, as well as the right side. So I'll say, yes, this is symmetric with respect to y equals x. How about y equals negative x? So if y equals negative x, then x also equals negative y. So I can take this y and make it negative x. And I can take this x and make it negative y. Now, can I algebraically make this match the original? So if I multiply both sides by negative y, negative times negative is positive, so it's yx equals, and then these cancel, negative 3, and then I can divide both sides by x, and I get y equals negative 3 over x, and the left and right side both match the original. So I will say yes, it does have symmetry with respect to y equals negative x. Okay, now parent function, f of x equals the square root of x. What transformations take place here? So first we look inside of the function. The function is this right here, the square root of x. Is anything done inside of that square root function? Yes, there's a plus 2. So the first thing is that it shifts left 2 units. Okay, there's nothing else inside the function, so we move outside the function. And there's multiplying first, multiplying by a negative. Okay, so when we multiply by a negative and it's outside, that's a reflection. And because it's outside, it's vertical, so it flips this way. So it's going to reflect or flip over the x-axis. Okay, then there's a positive 3, so there's 3 added to this function outside, which is vertical, so it is going to shift up 3. Now let's see if we did that correctly. So we'll go to y equals and put in the square root of x and graph it. Okay, now we'll go to y equals and down to line 2 and type in 3 minus the square root of x plus 2 and graph that. Okay, so it is shifted left 2. Okay, so it was here, now it shifts left 2. Then it flips over the x-axis, which would actually put it down here. But after that, it is shifted up 3 units. So it looks like we've got the correct transformations. Okay, then number 3, same parent function. Does anything happen inside of the square root function? Yes, it's multiplied, so that's a dilation. And it's inside, so it's horizontal. And inside, just like this moved left 2, we do opposites, we do reciprocals. So it's a horizontal dilation. And it is by the reciprocal, so it is by 1/7. So that means all of the x values get divided by 7. Then you go outside and there's a plus 2, so it shifts up 2. Okay, so let's graph that. So we'll go to y equals, we'll clear out y2 and type in the square root of 7x plus 2 and graph. It's going to be difficult to see the dividing by 7 part, but that would actually kind of make it go up faster. So it's a little bit steeper, and it shifts up 2 units.